Hello, 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 hello. So, okay. So there was, I think, a brief interruption in the lecture. There was some technical problems. So we will continue from here. Right. In fact, I was just starting about surface tension, and I was discussing that surface tension is a property of the fluid which arises due to unbalanced forces on molecules which are present near the surface of the liquid and air interface. Now, you must understand that any fluid molecule which is present in the bulk of the fluid, it is in a state of dynamic equilibrium, so the net force acting on it is balanced from all sides. But the same cannot be said about a fluid molecule which is near the surface, right? So there can be an interface between one fluid with some other fluid, or with fluid and air or some other gas, and fluid and solid. So there can be three kind of interfaces, right? Liquid liquid, liquid gas, and liquid solid. Though all of them will have a role to play, right? Especially when we are doing topics like angle of contact. I'm sure you are all aware of those topics. But when we talk about surface tension as such, we are mainly dealing with the unbalanced force at the liquid and gas. In our case, it will be liquid and air interface, right? So we'll just continue on the notepad. Just spare me a minute. Let me just start this. So, okay. Just spare me a minute. Let me just start the notepad. card is not opening. एक मिनट, एनी डेस्क आ रहा था एप्लीकेशन विंडो में तो क्लोज कर दिया, अब इसको वापस चालू करते हैं। जस्ट गिव मी वन मोमेंट। बंद होगा, कनेक्ट नहीं हो रहा है मुझे। हाँ हाँ हाँ, एक मिनट, हम, यस इट इज ओपन, कनेक्ट कीजिए। सर ओपन है ऑलरेडी, जस्ट हैव टू शेयर योर स्क्रीन। एप्लीकेशन विंडो में नहीं आ रहा था वो, विंडो में नहीं दिखता है क्या? नहीं दिख रहा है। शेयर एप्लीकेशन, अब दिख रहा है, अब नाउ इट्स सो देयर, ओके। सो यू आर ऑन, ओके। So apologies, right? Today we had a little bit of technical difficulties. So now we go, right? So we were talking about surface tension, right? So if you just think of a fluid, this is obviously not a diagram which is to the scale, right? So let us say this is the fluid molecule, and if I'm taking a fluid molecule in the bulk of the material like here, right, then well, it is attracted by other fluid molecules in all directions, and the resultant of this is of course equal to 0. As we said that if you take a fluid molecule in the bulk, then the net forces on it are completely balanced. On the other hand, if we take a fluid molecule which is on the surface, right, then on one side of it you will have the fluid molecules which are attracting it, right. At the same time, the air molecules will also have an attraction, but that attraction force would be very, very small. Again, I'm telling you, these diagrams are not to the scale, right? So this attraction of the air molecules is going to be negligibly small as compared to the attraction of the liquid molecules. So on this molecule, there is a net force which is inward, pointing towards the fluid, right? So this is the force which is responsible for surface tension, right? So the unbalanced force on the fluid molecule present near the surface gives rise to the phenomena of surface tension. I think I talked about earlier that if I take a molecule right here, so this molecule has interface with solid as well as fluid. So even it will be having some unbalanced force, right? And that unbalanced force, well, may have the solid, right, dominating the force, or it may have the fluid molecules dominating the force, depending on what kind of fluid we are taking and what kind of solid interface we are taking, right? Or it can also be a case that this fluid is in, let us say, in contact with another fluid here. So this is fluid 1 and this is fluid 2. Even here at the interface there is going to be an unbalanced force, which now could be upward or it could be downward, depending on what kind of forces the fluid 1 and fluid 2 molecules are exerting, right? So you must understand that this entire phenomena that we are studying, it is due to unbalanced forces. and these kind of unbalanced forces can arise at the liquid-liquid interface. It can arise at the liquid-air interface. It can arise at the liquid-solid interface. We'll be studying all of them, but mostly this chapter is about the unbalanced force arising at the liquid-air interface, right? And that is what we call surface tension. So what happens is that because of this unbalanced force, right? So I'm again taking the same example here, that we have this liquid surface. This is liquid air interface. So the molecules at the liquid air interface, we know they are acted upon by a net force in downward direction. So all the molecules here are acted upon by a net force in downward direction. Again, let me be very clear. I am not saying that there is a net external force acting on these molecules. No, no, no. If I take a molecule here, this molecule is in dynamic equilibrium. So the net force acting on it has to be zero essentially, right? But I am saying that the cohesive force, that is the molecules of the liquid, will have a net downward force acting on it, which has to be balanced by some other force so that it remains in equilibrium. So we are talking about a net cohesive force, or the net force on this molecule by the liquid molecules, which is in downward direction. So since all the molecules on the surface is acted upon by a net force in downward direction, a net cohesive force in downward direction, it leads to a sort of increase in pressure, or you can say that it leads to what we call formation of a thin film at uh, thin film at the interface, which is under some tension. So we have this two-dimensional thin film at the surface, and this surface comes under some tension, right? And the amount of tension present per unit length on any line drawn on the interface is called T or S and surface tension. So you must understand that surface tension can mean two things. One is the property of surface tension, and the other thing is surface tension may mean the numerical quantity, right? And what does it represent? That numerical quantity represents the force per unit length acting on any line drawn on the interface of liquid and air, right? And that interface acts like a tight film under a tension, right? So again, like if we see the top view of this diagram, right? So we'll just have a top view of this diagram. So if you see the top view, let us say it's a cylindrical vessel, this is the top view. So this is your film, right? So we can say this is the film. This is the film as seen from the top, right? And now in this film, suppose I draw any line. I just change color so that it is right. So suppose we draw a line here, right? So if you draw the lines here, then the liquids to the right of the lines will be pulling it, and the whole not just liquid, the entire thin film to the right is pulling it towards right, and towards left also it is pulling it left. So actually the net force acting on, if I draw a line, the net force acting on the line is equal to 0, right? But if I say the length of this line is L, then the resultant of the force in one direction is surface tension into L, and in the other direction is also surface tension into L. So this is what you need to understand, right? So surface tension is again something you must understand, which we are studying on a very qualitative scale, right? Surface tension is not something which you can derive, right? So can we derive the value of T, right, from other properties of the fluid, etc.? No, we can't do that, right? It's a bulk property, right? And its derivation is very tedious, right? It is completely outside our scope, right? And we are not interested in it. So, this chapter, in this chapter, sort of, we have to deal with use of the surface tension in different situations, right? So you must be aware of all those situations in which they can ask you the question, right? So this is one topic, surface tension, which well, it's not possible to have the same kind of conceptual grasp of this topic as any other topic of JEE syllabus, right? So whether it is mechanics or whether it is electrodynamics, right, including magnetism or EMI or AC or modern physics, right, any other topic, right? So we can have a conceptual understanding there to exactly what is giving rise to a certain phenomena, right? In surface tension, we only qualitatively understand that, okay, this phenomena is caused by unbalanced forces on the molecules near the interface, right? But we can't go on to numerically find how those unbalanced forces lead to T, right? This is something which is beyond our scope. So so to that extent, you can say that this is an experimental science that we are doing in this chapter, right? So now imagine that this is the top view of an interface, right? So maybe we have a cylindrical vessel full of water, and this is a top view of a cylindrical vessel filled with water, right? And in this we have, let us say, a pin, right? So we have a thin pin, right? So this is a pin, you can say the pin of length L, right? And this L is very, very large compared to R, which is radius of cross section of pin, right? And we can also have the mass of pin is equal to M. Now if this pin is very carefully, provided that the mass of the pin is small, right, and its radius of cross section is very small compared to the length, and if we very carefully put this pin over the surface of water, right, this pin is made of iron, which is much denser than water, but surprisingly it is found to float over the surface of water. So what exactly causes it to float, right? So like if you look at from here, right, so from this view, if you look at this, I am having a much enlarged view. So this is the cross section of the pin, right? So this is cross section of pin, right? And we find that just a moment. So this is your water surface as seen from here, right? So we find that this pin somehow it is just floating over water, right? And on this part I'm just very crudely drawing it, right? So but what we find here is that this water molecules, right, the film here would be applying a force on the pin. Just a moment. So it'll actually be like this. So this is a water surface, right? So a part of pin is inside water. If you look at here, I'll just change color and I'll show you. This part of the pin is inside water, right? And it does contribute to this contributes to a buoyant force, right? A difference in pressure inside and outside, which we will ignore. Right, we are ignoring it because the first thing is that the volume of fluid displaced would be very small. Second thing is that the density of the fluid is much smaller compared to the density of the iron which is forming the pin. So it would be a reasonable thing to ignore it, right? Though if the examiner has given you that, okay, the pin is exactly half submerged, then maybe you need to take this buoyant force into account. So when numerically it is possible to find the buoyant force, we will include it into our calculations. If it's not possible to numerically determine what buoyant force will act, then we will choose to ignore it, right? We will assume that is very small and we will continue as such, right? So now if you look at the forces here, then this is surface tension, right? I hope you can see that it is just the cross section of what we are doing here, right? It's a cross section of this. And so this force of tension is present over the entire length of this. So the actual force acting in this direction would be equal to T into L, and in this direction also it will be T into L, right? And maybe there is this angle with the vertical, we can say, is theta. So you can see the net upward force is 2TL into cos theta, and because of this, if it is floating, then this should be equal to mg. Here we are ignoring the buoyant force, right? So now here, what can be the maximum value of theta? Right, it can be any maximum value, right? So it depends on how large the tension is. Theta will be larger and larger, but what can be the minimum value of theta so that it just floats, right? So that brings us to theta equal to 0. That can be the minimum value of theta, in which case you simply have 2TL is equal to mg, right? So this would be the condition that or this is the mass, you can say this is the maximum mass of the pin of length L which can float. All right, so just a little bit of calculation, you can see that mass per unit length, lambda is equal to 2T by G, and this is the maximum linear density of pin to float, right? So here we were basically looking at the property of surface tension as the force acting per unit length on any line drawn on the interface of the liquid air surface, right? We'll just take another example. Imagine that we have this frame, right? This is a thin metal frame, right? And in this thin metal frame, we have, let us say, a soap solution, right? So maybe we have a soap solution here, right? And let us say that we have this movable pin, again of very small cross section compared to its length. So length is L, and length would be very small, very large compared to its cross section, right? So this is soap film. So now on this pin, I hope you can see that there would be a force of P into L acting due to the soap film, right? And if you look at the cross section, if I see the cross section from here, the top view, right, then you can see that there is a force, and this region is the soap film. This region is the soap film, right? This is the thickness of soap film that I am showing here, right? So you can see that here there would be a force of surface tension, and there would be a force of surface tension over the entire length of L, right, which is perpendicular to this or normal to this. So this force would be actually 2TL, right? So if you just leave the system, then what will happen is that the pin will move towards left, right? Pin will move towards left, and eventually the soap film will simply disappear, right? If you want to increase the length or the width of the soap film, we must apply a force in the opposite direction. This external force must act in this direction, right? So suppose this external force is exactly equal to 2TL. Suppose F external equal to 2TL, then what will happen is that the thin film can be moved slowly, or whatever velocity it will move with constant velocity. This pin will move, and the thin film will keep on increasing, right? So what will be the work done by this external force? W external. Let us say that this length is x, and W external in changing x from 0 to its current value. So when it was 0, it means that there was no thin film, right? So then this simply comes out to be, because this force happens to be constant, so you will get W external is equal to F external, that is 2TL into x. Now you can see that what is the area of cross section of this film? The area of this cross section of this film is L into x, but there are two areas. Like here you have an area of L into x, right? There are two interfaces. There's also L into x. So there are two interfaces. Okay, here I must tell you what interface mean. By interface we mean a layer which is hardly 8 to 10 molecules across. So even if you have a thin film, which would be a few microns, quite a few, right? Maybe it is hundreds of microns thin, right? But we are talking about a layer which is just 8 to 10 molecules across. So that would be of the order of nanometers. So there would be two such layers on both sides of the film, right? So the total area of the interface is not Lx. Total area of the interface is basically 2Lx. So if I write what is total area of interface, it will be equal to 2Lx. So if I use it, you have W external is equal to 2Lx into T, that is T into A. So what we are seeing here is that surface tension into area of the interface gives you the work done by external agent, which is equal to increase, because the kinetic energy is not increasing, right? There is no heat involved here. So some form of potential energy must increase, and we call it surface energy. And this would be equal to increase in surface energy. So it is not a general derivation of surface energy, right? So you can do a general derivation as well. Right now we are not interested. So this is, you can say, an indicative direction derivation, so that you understand what surface energy is. So now we are saying that surface energy of an interface per unit area is also equal to T. So this numerical quantity T, or surface tension, right, it can represent either the force acting on any line drawn on the interface per unit length, or as the amount of surface energy contained in the system per unit area of the interface, right? And let me again remind you that we are right now studying the property of only one kind of interface, the interface of liquid and air, right? So this T will depend on both which liquid it is and like the density of the air or whatever gas is there, right? So it will depend on that, and it will obviously depend on temperature as well, right? The surface tension, like the forces which give rise to surface tension, they are temperature dependent, and so the surface tension will also be temperature dependent. So we move to further examples. One straightforward example here will arise here, that find amount of heat evolved when some 1,000 droplets each of radius r, right, uh, coalesce to form a single drop of liquid. And let us say surface tension of the liquid air interface is equal to T. So what we'll do here is we'll just look at what is the decrease in surface energy. So the decrease in surface energy goes to heat evolved. Right, that's all. Decrease in surface energy would be equal to the surface tension into initial surface area minus surface tension into final surface area. That will be equal to heat evolved. Right. How do you find the initial surface area? It's very simple. Initial surface area is going to be A initial is equal to 1,000 into 4 pi r square, right? And A final equal to 4 pi capital R square. And how are they related? Well, you have to conserve the volume, right? The volume of the liquid when they coalesce will remain constant. So you have 1,000 into 4 by 3 pi r cube is equal to 4 by 3 pi capital R cube. So from here you have, this implies capital R would be equal to 4 by 3 pi will simply cancels out. So is it equal to 10 R. So if you substitute here, this would be equal to 4 pi into 100 R square, right? So you can see that heat evolved is simply equal to surface tension into the change A initial minus A final will be 4 pi r square into 1,000 minus 100, that is 900. So this is the amount of heat which has been evolved when this happens, right? So what actually happens is that this amount of heat first goes on to increase the temperature of the right single drop. So single drop will not be at the same temperature as the individual droplet, will have a higher temperature, and ultimately because that temperature is more than the temperature of the surrounding, it will be dissipated as heat, right? Next we come to the concept of excess pressure across a spherical or cylindrical surface, right? So once we have done it, we'll know what is the excess pressure inside a sphere, or what is an excess pressure inside a cylinder, hollow sphere, solid sphere, all those kind of cases we'll be able to handle here. So imagine that we have a liquid drop which is spherical in shape, right? And let's say that the pressure outside is P1 and the pressure inside is P2, right? So you must understand that in this FPD what we are doing, P2 is the pressure of the liquid and P1 is the pressure of the air outside, and we are doing FBD of interface of liquid air. So in our FBD we don't have the air, in our FBD we don't have the liquid, we only have the interface, right? So just one moment. On the left half, So that too, I am not taking the entire interface. I am taking only interface on the left half. So you have this interface, right? So this is our interface of the left half. So the diagram is not too good, but I hope it is clear, right, what we are drawing. So what is outside of this interface? Outside of this interface is air, and inside of the interface is liquid. So you must understand that there is only one interface. This is not a double interface. It's a single interface, right? And what is the thickness of this interface? As we already discussed, it is hardly 8 to 10 molecules thick, not more than that, which would hardly be a few nanometer. So we have basically a spherical cell of thickness of a spherical, not even a cell, half cell of thickness around 8 to 10 nanometers that we have in our system, and we are drawing the FBD, right? So first thing here to note would be that let me just change the color, right? First thing would be that from outside, effectively the net force of the air is P1. I have assumed the outside pressure to be P1. Just a moment. Yeah, so the outside pressure we have assumed to be P1. So this force is going to be P1 into 4 pi r square. And because of the liquid, the force on it will be equal to P2 into 4 pi r square. Right. And on the interface, both, right, on the outer surface, both on the outer surface, right. So on the outer surface, everywhere we have a force in this direction, and that is equal to T. This entire length is 2 pi r. So 2 pi r into T is the force acting in this towards right, and this force acts on the outer surface at the interface, basically, right? This force acts at the entire interface of air and liquid. So obviously this interface is in equilibrium, net force on it will be balanced. So if you just balance them, you have P1 into 4 pi r square uh, plus 2 pi r into T is equal to P2 into 4 pi r squared. So if you just solve, you will get P1 is equal to P2 minus 2T divided by R. Right. So you can see that P2 is greater than P1, and the pressure difference is 2T by R. So you must understand that what is P2 here? P2 is pressure on the concave side of interface is more than pressure on convex side of interface. It's important to understand that it's not that the pressure of liquid has to be more than the pressure of the gas. No. What we are doing is that pressure of the concave side is more than pressure of the convex side, because in the same problem, if I make a change and I say that there is a liquid outside this and it's an air bubble inside liquid, there is liquid outside and air inside, nothing will change in this entire calculation. We'll still get P1 would be less than P2. So it doesn't matter whether you have a like interface in which liquid is on the concave side or on the convex side, right? So it doesn't matter. It's not dependent on which side liquid is. It simply depends on which side is concave and which side is convex. The concave side would be at the higher pressure and the convex side would be at the lower pressure. If you have liquid at concave side, liquid is at higher pressure. If you have liquid on the convex side, then liquid is at lower pressure, and the pressure difference across every surface is 4T divided by R. Now if I was doing the same thing for, let us say, a cylindrical surface, right? So let us say that we have a Right, so we have the cylinder, long cylinder, right, which means L is very, very large compared to R, and we ignore the edge effects. Ignore edge effects. If they say long cylinder, then that is obviously the assumption that they have in mind, right? So if we have this case, L is very, very large compared to R, right, then we can comfortably ignore the edge effects, right? And now I'll do the same thing. I'll take FBD of interface of liquid air in half of cylinder, and I'll draw the top view. It will appear exactly in the same way. The only difference is that now the cross section is, there's not a cross section of a sphere, it's a cross section of a cylinder. And again, if I say outside pressure is P1, inside pressure is P2, we have exactly the same thing here, right? In this direction, the forces due to the air outside, maybe, right, let us say outside is air and inside is liquid, or vice versa, no, makes no difference. So the force is P1 into, well, this area, this entire area, right, which I am showing here by the shaded, this area of the half cylinder, right, its projection would be equal to pi r into L, where r is the radius of cross section of the cylinder. I think I have used small r for that, so we'll use the same thing, no issue, right? So pi r into L is the length of the shaded half cylinder, sorry, area of the shaded half cylinder, and from inside there would be a force of P2 into pi r into L. And again, at the interface, everywhere at the interface there would be a force, right? So here there would be a force, right, T, and here also T into L, and even here there's going to be a force of T into L, and this interface is again in equilibrium. So if you equate the forces, you will have P1 into pi RL towards right plus 2TL is equal to P2 into pi R. Just give me a moment, there is a small mistake. Will okay. So like the mistake was that we had to take not the total area of this, right? We have to take the projected area. Total area indeed is pi RL, but the projected area would be equal to 2R into L, right? And even here the projected area would be 2R into L, right? So P1 into 2RL plus 2TL, P2 into 2R into L, right? So you must understand that why are we taking the projected area. Even in the previous case, I'll remind you, we had taken the projected area, right? This is something which we had done in fluids, right? That the resultant of all these forces due to the pressure of whatever is outside, air or liquid, the resultant of all this is not going to be P1 into this total surface area. It is going to be P1 into the projected surface area, right, which in this case is again we had a mistake here, right? In this case, this projected area is going to be, so it was a common mistake we were doing, right? P1 into pi r square, even here it is P1 P2 into pi r square, right? So we have to take the projected area as the resultant of that, right? So okay. So solving, what we get here is P2 is equal to P1 plus T divided by R, right? So again, we are seeing that the pressure on the concave side, this is the concave side, the pressure on the concave side is more than the pressure on the convex side. The difference of pressure is T by R. So that leads to us to a right, fairly very simple condition, which is very easy for us to remember, right? The condition is that whenever there is an interface between any liquid and air, then the pressure on the concave side of the interface is always more than the pressure of the convex side. And if the interface is spherical, the value of excess pressure is 2T divided by R, and if the interface is cylindrical, the value is T divided by R, right? So we will continue from here. So example, right? Some things, some, if we have, let us say, a liquid drop in air, right? Or if we have an air bubble inside liquid, in both these cases there is excess pressure on the concave side, which is inside the drop oblique bubble. So it doesn't matter, right, whether you have air in the drop and liquid outside, or whether you have liquid in the drop and air outside, the pressure inside that sphere is going to be more than pressure outside. And by how much? It is equal to 2T divided by R. But if we have air bubble in air, right, so you must understand what is happening here in case of air bubble in air, right? So this is it. So you have liquid, so you have liquid here, right, a thin layer of liquid, and air outside and air outside. The question is how thin? How thin is this layer? How thin is this layer? So this is few microns, right? A micron is 10 to the power minus 6 meter. So this could be 10 micron, 20 micron, even 100 micron. And what is the thickness of an interface? I told you earlier that is around 8 to 10 molecules, that is around 10 nanometer, right, or so. So you have two interface, right? So you have, this is inner interface, and here you have outer interface. So in this particular case you have two interface. So if I say pressure is P, then pressure here is, it's on the concave side of the air liquid interface. So pressure here will be P plus 2T divided by R, and pressure here again, if we take, then it's going to be pressure at this particular point plus 2T by R. So it will be P plus 4T divided by R. So we can see again that the pressure in of the air which is inside the bubble is going to be more than that of outside, and the excess pressure is 4T divided by R. Next topic we'll be doing is angle of contact, right? So earlier I told you that there would be additional forces, right, unbalanced forces at all kind of interface, whether it is liquid air interface, or whether it is liquid solid interface, or whether it is solid air interface. There are going to be unbalanced forces at all interfaces. We till now we dealt in detail with the interface of liquid and air. Now we'll be dealing with all the interfaces, and because like all the interfaces will have a role to play in getting the angle of contact. So imagine that we have a container, and I'm assuming that this is a very narrow container. So if I say this is R, then I am assuming that R is very small. With this assumptions we are working, right? So now we don't know how the surface is, right? So this is liquid inside and air outside, and this is a solid container, right? This is solid container. So you can see that we have all interfaces in play, right? At this point you have air and liquid interface. At this point you will have solid and liquid interface. In particular, if we come to this particular point, so it is in contact with all three, that is solid, air, as well as liquid. Now here, the force due to solid. So this is a molecule of fluid, and on this I am showing force due to solid. Right, force due to air is so small that we can simply ignore that, so we will keep on ignoring it. And then here you will have force due to liquid. Right, so now force on molecular fluid, because of molecular fluid, this is given a name, cohesive force. And force of molecular fluid due to molecules of solid, we give it a name, adhesive force. Right, so now if you look at the resultant of the cohesive and the adhesive force, right, if you look at the net force, the magnitude as well as direction, so that will obviously depend on which is the larger force, whether adhesive force is the larger force or whether cohesive force is the larger force. Right, so we'll deal with both the cases. Let us say in this case that the adhesive force dominates. So if the adhesive force dominates, then maybe just a moment, I'll use a different color, it will be easier. So we are assuming that the adhesive force is dominating, and so this is the net force, net of the uh, cohesive and adhesive force. We have ignored the force of air, and we have also ignored the weight of the liquid molecule. Maybe you can even take them into account, and let us say this is the net force. So if this is where adhesive force is having more to say, right? What if cohesive force have more to say, right? What if we have a case where cohesive force will dominate? So then maybe I'll draw the diagram for that case. So this is the presumptive surface. I'm not saying this is a surface. So we have a molecule here, and this is the adhesive force, and we have a very large, let us say, cohesive force. So in this case, the cohesive force will dominate. So the resultant force would be more like this. This would be something like F net. Right, now you know that the liquid cannot have any unbalanced force along the tangential direction, because it will actually move. The only direction in which there is an unbalanced force and still the liquid will not move is inward. Right, if you have a unbalanced, if you have apply a force inward on the surface of the fluid, it won't move because the fluid is right, quite incompressible normally. Right, so it won't actually move. There would be some other elastic forces which will balance it. So the only direction in which we can have the unbalanced cohesive and adhesive force is perpendicular to the interface. It means that this F net has to be perpendicular to interface. Right, so this is the direction of the interface. Right, so here the interface has to be something like this. And the other case, so here this was the F net, here the interface has to be something like this. So you can say that, like, we are not numerically doing that, okay, F cohesive is more than F adhesive equal, or no, not like that, but we are saying that when adhesive forces are dominant, right, if adhesive forces are dominant, please concentrate on the language. I'm not saying if adhesive force is more than the cohesive force, no, I'm saying adhesive force is utterly dominant, then interface is concave from outside. And in this case, if cohesive forces are dominant, interface is convex outward, right? And we'll next define the angle of contact, right? So angle of contact is defined to be the angle between a line which goes into the fluid, right? One line which goes into the fluid and the other line goes along the interface. The other line goes along the interface. So this angle is called angle of contact. So when adhesive forces are dominant, you can see theta is acute angle. And when cohesive forces are dominant, you can see theta is obtuse angle. Okay. So in all these examples, you might have noticed that I'm showing that the adhesive force is acting exactly perpendicular to the container, right? So it is acting perpendicular to the surface. What was the logic behind it, right? So that is again something which you can have a look. It's like this. Let us say this is a liquid molecule at interface. This is the molecule for which we wrote the FBD here, right? So all these FBD is written for this, sorry, it is written for the molecule here, right, which is a liquid molecule on the interface. So we are again dealing with it. So I am taking the liquid molecule on the interface. And on one side of it, you have a lot of solid molecules. So let us show solid molecules by some particular color. So these are solid molecules on one side of it, and right, so you have solid molecules on one side, right? A large number of solid molecules, right? In this direction it extends. Even if the solid is of very small thickness, the number of molecules will definitely be very, very large, in millions, right? And in this direction also practically up to infinity, right? As far as this molecule is concerned, very, very large. In this direction also very, very large. So I hope you can see that the resultant of the force of attraction of all these molecules on this net force of attraction by symmetry would be in this direction, right? Could you think a situation when this symmetry would be broken, right? This symmetry would be broken only when the liquid molecule at the interface is not in the middle of the solid like here, but it goes to the top. If the molecule of the interface, it goes here, then there is no symmetry. Then we can't say that F adhesive has to be in this direction. For this F adhesive could be in this direction, it could be in this direction, it could be in this direction, it could be in this direction, right? So when the direction of adhesive force changes, then this angle will also change, right? So this angle which we are saying angle of contact, this angle of contact is a constant characteristic of the liquid and solid involved, right? But only as long as level of liquid does not rise to the top, right? Once the liquid rises to the top, then this angle can change, right? So this angle can self adjust, you can say, or change once liquid layer rises to the top of solid container. So we'll be right. We'll be concluding the lecture here, right, and we will continue this lecture, right, because we have another one small topic left in surface tension, and that topic is capillary rise, right, and then we have to do a little bit of elasticity and a little bit of viscosity, which will be taking which will be doing in the next lecture tomorrow, right. So that's it for today. I would suggest you to go to HC Verma, and you can do the illustrations there in surface tension. We have quite a good number of illustrations there. So you can do that, or you can just go and revise whatever material, the Chaitanya material you have, you can revise that. So whatever you have done earlier in your regular classrooms, right, I would suggest you to go and revise all those illustrations, right. And surface tension is something which you have to practice, and the different cases you have to remember, right. So this is a chapter which has quite a different approach compared to the other chapters which we have been dealt in now. Okay, so thank you. So thank you. So we'll meet tomorrow to complete this lecture and to conclude with the remaining topics of properties of matter, elasticity and viscosity.